All right, guys. Welcome to Friday's lecture. This is a little bit awkward lecturing into a camera instead of a room full of people, but hopefully this will work out okay. This lecture should be viewed after Thursday's lecture, but before the following week's lectures begin. So ideally Friday morning or over the weekend. All right, don't forget, you guys have recitation on Friday at the usual time as well. All right, so today we're going to cover potential energy, but before we do, let's do a quick review of what we know about work and kinetic energy, right? So remember, first of all, that for a constant force, the work done is force dotted into displacement. All right. For gravity, this expression became the work done by gravity is equal to minus m times g times delta y. For the spring, the work done by spring is minus 1/2 k times x2 squared minus x1 squared. For the normal force, we found out that the work done was 0, but this is only for sliding objects. Remember that if an elevator is moving upwards and there's a box on the floor of the elevator, the normal force of the elevator floor in the box is doing work. Okay, so I'm only talking about objects sliding across surfaces. In those cases, even if the surface is curved, the work done by normal forces is 0. And then finally, tension. The work done by tension is also 0, but this is for swinging objects. If I pull an object across the table by a string, that represents a situation where work done by tension is non-zero. Okay, I'm talking about an object swinging back and forth like a pendulum. In that case, work done by tension is 0. Okay, so most importantly is the work energy principle. Which states that the total work done on an object is the change in kinetic energy of the object, where kinetic energy is 1/2 mv squared. All right, so what I'm now going to do is I'm going to divide our forces into two groups. I'm going to divide forces into conservative forces and non-conservative forces. And what exactly does that mean? A conservative force is a force whose work depends only on the initial and final positions of the object. So this is an unusual definition, and what does this mean exactly? A conservative force, all forces can do work on an object, but what we're saying particularly about the conservative force is it doesn't matter how we get from point A to point B. If you know what the initial location is of the object and what the final location is of the object, then that is enough to determine what the work is that's done by the force. Okay, so let's take a look at our forces. Let's look at gravity. So gravity, the work done is minus mg times delta y, which is minus mg times y2 minus y1. This says that if the object starts out at an altitude of y1 and ends up at an altitude of y2, we know exactly what the work is that's done by gravity. We don't know anything how he got from y1 to y2. And we don't need to know how we got from y1 to y2. We can overshoot and then come back down to y2. We can go in a straight line. We can go in a curvy line. It doesn't matter. If you know the initial value of y and the final value of y, then done. You know what the work is that's done by gravity. So this follows the definition of conservative forces. So gravity is conservative. Okay, what about spring force? The work done by spring force is minus 1/2 k x2 squared minus x1 squared. And as you can see, once again, if you know what the initial position is of the mass, remember x is the amount by which the spring is stretched or compressed, and you know the final value of x, it doesn't matter how you got from x1 to x2. Just knowing what x1 is and knowing what x2 is enough for you to be able to calculate the work done by the spring. So that means spring force is also conservative. All right, well, what about normal force? And tension. Well, you might say, well, okay, we know these forces produce zero work. And that's not true. As I said before, it's possible to have situations where normal force does non-zero work and where tension does non-zero work. And it's a little bit difficult to explain, except for the fact that plain and simply you can come up with an example. It's a little bit contrived, a little bit weird, where normal force does work on an object, bringing it from one location to the other, but that work is what we call path dependent, meaning that it depends on how we get from point A to point B. That if we go in a straight line or if we go in a squiggly line, we're going to get different values. So plain and simply, normal and tension are non-conservative forces. All right, well, how about friction? One more. Is it conservative or is it non-conservative? Well, if I take a box and I push it across the table, okay, from here to here, from point A to point B, the work done by friction is going to be the force of friction times the displacement times the cosine of the angle in between the two. Cosine of 180 is -1. So I end up getting minus the force of friction times the distance traveled. If I start here and take a different path, forwards, over, and back, now I've traveled a greater distance. Is the work done by friction the same, though, if my starting and end points are the same? And the answer is no. I've traveled more distance. The more the object slides, the more the work is that's done by friction. And that's because as I change direction of sliding, friction is always pointing in the opposite direction of the motion of the object. So I'm always going to get minus the force of friction times the distance, minus the force of friction times the distance, minus the force of friction times the distance. I'm not going to make up for it by changing directions. So the more distance I slide, the more work is that's done by friction. So I'm going to get one value if I go this way, another value if I go this way, another value if I go all the way around and back. So the point is that friction is a non-conservative force. Okay, so we've broken our forces into groups. We have two forces that are conservative, and all the other forces that we've talked about until now are non-conservative. So what do we do with this? Well, it turns out that for non-conservative forces, for conservative forces, there is an associated potential energy. So that means we can talk about gravitational potential energy, we can talk about spring potential energy, but we can't talk about normal force potential energy or tension potential energy or frictional potential energy. They simply do not make any sense. And how do we define the potential energy associated with a force? Well, you do that in the following way. The work done by a conservative force can be written as the negative change in potential energy, where U is what we're defining as potential energy. So this might not seem like we're saying much here, but let's take a look at what this says about gravity, for instance. So we know that the work done by gravity is equal to minus mg delta y, which can be written as minus mg times y2 minus y1, which is minus mg y2 minus mg y1. So from here, you can see that if we defined gravitational potential energy in the following way, if we said that U, gravitational, was equal to m times g times y, then what would delta, the change in gravitational potential energy, be? Well, it would be mg y2, or let's say, right, this is u2 minus u1. u2 would be the potential energy at position 2, which will be mg y2. And u1 would be the potential energy at position 1, which would be mg y1. So as you can see here, the work done by gravity would indeed be minus the change in gravitational potential energy. So that means that this expression for gravitational potential energy actually does a great job fulfilling this condition that work done by gravity must be equal to minus delta U. Now, this isn't the only answer. In fact, this would also work if I wrote down mgy plus 5 or mgy minus 3, right? mgy plus a constant works because then mgy2 becomes mgy2 plus a constant. This becomes minus mgy1 minus a constant, and we still get the condition that delta U sub g is minus delta U sub g is the work done by gravity. So really there is an arbitrary constant here that we can add to this, but we're just going to set that constant equal to 0 so that we get the simplest, nicest form for gravitational potential energy. All right, so gravitational potential energy is m times g times y. Okay, so we'll go back to this in just a moment. I want to do spring potential energy as well, and then we'll go and take a look at what it means to increase or decrease the potential energy of an object. So for spring, the work done by the spring is minus 1/2 k x2 squared minus x1 squared, which can be written as minus 1/2 k x2 squared minus 1/2 k x1 squared. And so it's hopefully obvious what the expression for the spring potential energy should be. You can see that it makes sense to have it be 1/2 kx squared. Then delta U sub s is just U2 minus U1, which is 1/2 k x2 squared minus 1/2 k x1 squared. And then you can see that the work done by spring is minus delta U sub s. But again, if we added any arbitrary constant to U sub s, this would also work. But in order to keep our expression as simple as possible, we're going to set that constant to 0. Okay, so this is the spring potential energy. So what does it mean? Okay, what can we do to increase the spring potential energy? Let's start with that. How do we increase the spring potential energy of an object? Well, as you can see, the U spring, if I plot it, it's at a minimum when x is equal to 0. That means if the spring is neither stretched nor compressed, the spring potential energy is 0. If we stretch the spring, the more we stretch it, the more we increase the potential energy. Same thing happens if we compress the spring. Okay, so either way, whatever you do to the spring from its equilibrium length, whether you stretch it or compress it, you increase the potential energy. Okay. What about gravitational potential energy? Well, now, remember, U sub g is equal to mgy. So very simply, this is a linear function. And basically, the gravitational potential energy is equal to 0 when y is equal to 0. So that, of course, is going to depend on where the origin of your coordinate system is, which isn't a problem because you might be thinking, well, isn't that arbitrary? Can't we choose y equals 0 to be anywhere? Yes, that's true. But don't worry about it. It's going to be okay. So y is equal to 0. At whatever point we define to be y equals 0, that's where the gravitational potential energy is 0. If you go up, the potential energy increases. If you go down, the potential energy decreases. Yes, gravitational potential energy can be negative. Okay, it's not a problem. It's not a big deal for potential energy to be negative. It's weird for kinetic energy to be negative. 1/2 mv squared can never be a negative quantity, but gravitational potential energy can be negative. All right. So now, we're not going to do this for normal force or for tension, simply because we can't. Okay, if you tried to do the same thing, write the work done by, or friction, or work done by friction, you simply cannot write it as something minus something, right? So we can't assign potential energy to be one of those terms. It just doesn't work out. So good, we'll stop here. And what I'm going to do is I'm going to write the work energy principle down again, except now I'm going to write it in a little bit more detail. So here it is. Work total is the change in kinetic energy. But now I'm going to write down work total as work done by gravity plus work done by spring plus work done by normal plus work done by tension plus work done by friction is equal to delta K. And again, I realize that in most cases these guys are both zero, but I want to be as general as possible and talk about situations where even those works are not zero. And I'm going to actually lump all of these guys together into something called WNC, which is the work done by non-conservative forces. All right? So, work done by gravity, I can write as minus the change in gravitational potential energy. The work done by spring force is minus the change in spring potential energy. Plus work done by non-conservative forces, I can't do anything about that, I've got to leave it like that, is equal to the change in kinetic energy of the object. All right, let's write this as UG2 minus UG1. Right, change in gravitational potential energy is going to be the final minus the initial potential energy. Same thing for spring. And then finally, I'm going to write out delta K as K2 minus K1. And now I'm going to bring all the one stuff to the left-hand side and all the two stuff to the right-hand side. So all the one stuff, we get K1 plus UG1 plus US1 plus work non-conservative is equal to K2 plus UG2 plus US2. All right, so now we're going to simplify this a little bit by redefining some terms. So let me rewrite that. Oh, I'll put this down. So K1 plus UG1 plus US1 plus work non-conservative is equal to K2 plus UG2 plus US2. So now what I'm going to do is I'm simply going to define U as the total potential energy, meaning gravitational plus spring. Okay. So then this tells me what? This becomes K1 plus U1, UG1 plus US1 just becomes U1 plus work non-conservative is equal to K2 plus, this just becomes U2. We're done. Now I'm going to define, so this is the total potential energy. Now I'm going to define another quantity called E, which is equal to the kinetic energy plus the potential energy of the object. And we call this total mechanical energy. The total mechanical energy of the object is equal to its kinetic energy plus its spring potential energy plus its gravitational potential energy. So what does that then become? Well, now K1 plus U1 can be simplified as E1 plus work non-conservative is equal to E2. And although this is a correct statement and we are going to be using it at some point, I want to simplify this a little bit further by making an assumption. And that assumption is that this WNC is really annoying because we would otherwise have a nice symmetric equation here. So what am I going to do? Well, I'm going to say if WNC is equal to 0, then E1 is equal to E2. Or in other words, total mechanical energy does not change. So this isn't saying that non-conservative forces aren't acting on the object, but what it is saying is that they don't do work on the object. So not a problem if your object is sliding or swinging, but if you have friction acting on the object and the object is moving, odds are that friction is doing work on the object. So this really places a restriction on and basically says that there can't be any friction acting on the object. So if we have a frictionless situation, then mechanical energy is conserved, right? As an object moves from one point to another, then we have a situation where the total mechanical energy does not change. Okay, so this actually is called conservation of mechanical energy. Okay, so let's use it. Let's do an example. All right, so let's suppose that we have a mass that is pushed up against a spring, pushed up against a platform, I should say, that's connected to a spring. All right, and let's say that the mass is 10 kilograms. Let's have the spring constant be 300 newtons per meter. And my question is, let's have this be position 1 over here. Let's have this be position 2 over here. And let's have this here be position 3. At position 2, this mass is moving across with a velocity v2. The velocity here is v1, is 0. And the velocity here is 0. So this compressed spring is going to expand until it reaches equilibrium length. It's going to push this block, giving it a velocity. I want to know what V2 is, and I want to know also what H is. I want to know how high this mass slides up this incline before it comes to rest. Okay. So the initial amount of compression of the spring is, let's say, 80 centimeters. What is the speed of the mass after it leaves the spring? And how high does it slide up the incline? Okay. All right, so what are we going to do here? We need to figure out in all three of these cases what the kinetic energy is and the potential energy is of this mass. Okay, so we're going to need a chart. So let's take a look at different points. Point 1 at position 1, at position 2, at position 3. I want to know what K is. I want to know what U gravitation, U spring, and then the total mechanical energy. All right, so at position 1, what is the kinetic energy? Well, we're assuming it's starting from rest. So initial kinetic energy is 0. What is the initial gravitational potential energy? Well, K1 is 0. U gravitation, we can define y equals 0 to be the starting point of the object. So Ug is going to be mg times 0, or 0. And U spring is going to be 1/2 times 300 times minus 0.80 squared. Right, because the spring is compressed by 80 centimeters. Which is what? 1/2 times 96 joules, right? By the way, not sure if I mentioned this, but potential energy, all energies are in units of joules. Kinetic, potential. So adding all these up, I get 96 joules. That tells me that the initial total mechanical energy of the system is 96 joules. Now, as you can see, none of it is kinetic or gravitational. It's all spring potential energy. Now, what if we look at the second position? At this point, the mass is moving to the right. It has left the spring. So the spring at this point is not stretched or compressed, so there's going to be no spring potential energy, no gravitational either. All of the energy is going to be kinetic. 1/2 the mass, which is, what did we say it was? 10 times V2 squared. So what is the total mechanical energy here? Well, I end up getting this plus this plus this, or just 5 V2 squared. All right, and finally, so as you can see, at this point, it's all kinetic energy, no gravitational or spring potential energy. Finally, at the top of the incline, it's not moving, right? It's going to have a final y value equal to h. So U gravitation is going to be m times g times h, or y, which is h, and again, no spring. So adding these guys up, we get 98 times h, and we're done. Okay, so at position 1, the energy is 96 joules. At the position 2, the energy is 5 V2 squared. At position 3, the energy is 98 H. But conservation of total mechanical energy says that these three things must be equal to each other. E1 must be equal to E2. So that tells me 96 is equal to 5V2 squared, which gives me a V2 of 4.38 meters per second. Meanwhile, I can say E2 is equal to E3, or E1 is equal to E3, or whatever. All three of these mechanical energies must be the same. So let me just say that E1 is equal to E3, and that gives me 96 is equal to 98H, which gives me that H is equal to 0.980 or 98.0 centimeters. And we're done. The principle of total mechanical energy helped us solve this problem. It's important to understand when you can apply this and when you can't. As this mass is leaving the spring and sliding across the surface and going up the incline, there is, I should have specified this before, no friction, right? No friction. It's a sliding object, so that means normal force does no work. Tension doesn't even enter the picture, and it's a frictionless surface, so we have no friction, so we can apply conservation of mechanical energy. So once again, notice that we started off entirely with spring potential energy, then that energy was converted into kinetic energy, which was then converted into gravitational potential energy. So sort of think of this as we have different beakers filled with different amounts of water. You can pour water from one beaker to another, but you always have the same amount of water. It's the same thing with energy. You can convert from one form of potential energy into another, or from potential energy into kinetic, right? but these guys all must add up to the same amount. You cannot annihilate total mechanical energy or create total mechanical energy if there's no work done by non-conservative forces. All right. Let's do another example. Suppose a mass is released from rest. Let's have this be a 5 kilogram mass. Let's have this spring constant be 200 newtons per meter. And let's suppose that this is equilibrium length, meaning the spring is neither stretched nor compressed. So what I'm going to do is I'm going to drop this mass. I'm going to release it from rest. And I want to know how far does it go before once again coming to rest. So if we release the mass from rest, how far does it drop before again coming to rest? We'll drop down to a certain point. So we're going to say V1 is equal to 0 and V2 is equal to 0. Okay. So at this point, we don't really need a chart because we're talking about two different points here. We don't have to get too fancy. But let's just say that E1 is equal to E2, which is K1 plus UG1 plus US1 is K2 plus UG2 plus US2. Okay. Where I've split up U1 into UG1 plus US1. So K1 and K2 are both equal to 0. What is US1 equal to? Well, if the mass starts out at equilibrium length, US1 is going to be 0. However, if this thing expands by, let's call this amount capital H, then US2 is going to be 1/2 times 200 times capital H squared, 1/2 kx squared. What about UG1 and UG2? Well, it all depends on where I define my y to be 0. I can define it to be 0 here or here. If I take y to be 0 here, then my gravitational potential energy is going to be 0 here, but my initial one is going to be m, which is 5 times 9.8 times h. Okay. So then what do I have? K1 plus US1 plus 5 times 9.8 times h is equal to K2 plus US2 plus ug2. So simplifying this, I get 5 times 9.8 is 49h minus 100h squared is equal to 0. Or I get h times 49 minus 100h is equal to 0. So one of the answers for h is that h is equal to 0, which is obviously the answer we don't want. The other one is that h is equal to 49 over 100, which tells me that h is equal to 0.49 meters. This thing will drop 0.49 meters before coming to rest again. Now, is it just going to come to rest here and that's going to be the end of it? No, it's going to move back up again. In fact, it's going to oscillate between these 2 points, up and down. Why is it not going to come to rest here? Well, just because the velocity is equal to 0 doesn't mean the acceleration is equal to 0. In fact, there's going to be a net force upward at this point. So by no means is this mass going to drop down to here and stay here. Okay, but we did figure out that it is going to drop a distance of 0.49 meters. Okay. So what happens if work non-conservative is not equal to 0? What if, for instance, friction is in the picture? Or what if, for instance, a mass is being pulled by a string instead of the mass swinging? So how do we handle something like that? Well, what I'm going to do is go back to our problem. And let's redo it. But I'm going to do something different. It's going to be too difficult if I include if I simply say that friction exists everywhere, because especially as this mass churns up this incline, the normal force is going to get difficult to calculate, and therefore the force of kinetic friction is going to become difficult. So what I'm going to do is I'm going to say that there's going to be a patch of ground, and this patch of ground is going to be 1.5 meters long, and the mu kinetic for this patch is equal to 0.4 and is 0 everywhere else. So we have a mass pressed up against a spring. The spring constant is 300 newtons per meter. The initial compression of the spring is minus 0.80 meters, and the initial velocity is 0. the final velocity up here, v2, is 0. And we know what the answer was before, right? The answer before was, what do we get for h? 0.980, right? So now we suspect it's going to be not as high. So, and why? Well, because this friction-y patch is going to slow the object down as it's sliding over it. Okay. So let's take a look at mechanical energy here. We have K1 plus UG1 plus US1 is equal to K, is not equal to K2 plus, this is equal to, we have to, plus work non-conservative is equal to K2 plus UG2 plus US2. Okay. So starts off with 0 kinetic energy, 0 potential energy. The spring, so gravitational, the spring is 1/2 times 300 times minus 0.80 plus the work done by the spring, by the friction. We'll get back to that. That's equal to final kinetic energy is 0. U gravitational 2 is equal to m. Again, this is a 10 kilogram mass from before. So it's 10 times 9.8 times h, plus u spring 2, which is 0. At the top, it's not going to be stretched or compressed, the spring. So we need to, if we set these guys equal to each other, all we're going to get is the old expression. By the way, it's a squared, sorry, squared. All we're going to get is the old expression, which gives me that h is 0.98. And that's not what we want. Okay, so what do we do here? We need to find work done by non-conservative. Well, so let's imagine that the block is sliding to the right across a surface where there's friction. And as it goes from here to here, it undergoes a displacement of 1.5 meters. And what is the force of friction going to be on this thing? Well, for horizontal motion, we know the normal force and gravity are going to cancel each other out. So the force of friction is acting back in this direction. And the force of kinetic friction is equal to mu kinetic times the normal force, which is mu kinetic times m times g. All right. Normal force, it's hard, again, it's horizontal movement. The upward normal force cancels with the downward force of gravity. So the work done by kinetic friction is the force of kinetic friction times the displacement d times the cosine of 180 degrees. So this is minus mu kinetic mg d. The minus sign comes from cosine of 180. So this is what? Mu kinetic is 0.4, m is 10, g is 9.8, and d is 1.5. So this gives me uh, 58.8 minus 58.8 joules. That's what goes up here. So, now what do we get? Well, clearly, I'm sorry, this is negative. So, rewriting this, remember this is 96, right? So 96 joules minus 58.8 is equal to 10 times 9.8 times h. So solving for h, the left-hand side becomes 37.2. You divide that by 98, and you get 0.3796 or 0.380. Definitely less. Okay. Now, in the previous example, when we didn't have friction here, this thing was released, it slid across a frictionless surface, went up to a height of 0.98 meters, and then what happened? It just stayed there? No, you can't have a mass on a frictionless incline just stay there. Gravity is going to pull it back down again. It's going to go back down, and it's going to hit this spring, and it's going to cause this spring to compress by 80 centimeters. Then what's going to happen? It's going to leave the spring, go back up to 0.98 meters, come back down, cause the spring to compress, back and forth forever and ever and ever. And this would go on forever and ever and ever if there were indeed no friction, no air resistance, nothing. If really and truly the only forces acting on these things, on this mass, that did work was a spring and gravitational force, this thing would go on forever and ever. However, in the example where we include friction, is that what happens? Well, it goes across this frictiony path and now goes up to a height of 0.380 meters. But every time it goes off over the path, it's going to lose 58.8 joules of energy. So when we get to the top over here, we're not going to have 96 joules. We're going to have, instead, 37.2 joules of energy. So what's going to happen to this thing when it slides back down the incline and goes back across the frictiony path? Is it going to make it all the way across? Well, no, because every time you pass over this patch, you lose a certain amount of energy. Specifically, you lose, why can't I not remember this number? 58.8 joules of energy. So you can't have 37.2 joules of energy and expect to make it all the way across this patch. It's going to stop somewhere on this patch on the way back. So this thing will not go back and forth forever and ever. In fact, it will go once up here, and then on the way back down, it'll stop in midway through the patch. Or it won't make it all the way across. Okay, so mechanical energy is not conserved here, right? E, which is kinetic plus potential energy, is not conserved, and that is because we are allowing friction to do work on this mass. Okay? Now, it's important to state that even though mechanical energy is not conserved in this system, energy is still conserved. Okay, there are other forms of energy besides mechanical energy. And what in fact is happening as this mass slides across this incline? What is friction doing to the mass? It's causing the mass to slow down, but where is that kinetic energy going? Well, what happens when you rub your hands together on a cold day? You notice that friction causes the temperature in your hands to go up. And what does temperature mean? Well, temperature is a measure of the internal molecular kinetic energy of an object. So as this block slides across this surface, what will happen is its temperature will go up a little bit. But the internal energy of the object, which is the energy due to the molecular jiggling of the object, does not qualify as one of the components of total mechanical energy. So we say that total mechanical energy is lost. However, energy, if you include total mechanical energy and internal energy, is still conserved. Okay, so it's important to realize that you can't, I'm saying this with my fingers crossed behind my back, you can't annihilate energy. It isn't like friction is this magical force that can take energy and destroy it. What it can do is it can destroy mechanical energy, but that's only because it's converting it into a form of non-mechanical energy, in particular the internal energy of the object. Now, having said that, that you cannot annihilate energy, or for that matter create energy, that's actually not correct. According to Einstein and his famous equation E equals mc squared, as it turns out, energy can be created or annihilated according to the equation E equals mc squared. If you were to convert 1 kilogram of mass, m equals 1, into energy, you multiply m by c squared, where c is the speed of light, 3 times 10 to the 8th meters per second, and you get the equivalent energy. So you can eliminate 1 kilogram of mass, but you will be creating 1 times 3 times 10 to the 8th squared, or 9 times 10 to the 16 joules of energy as a result. Okay, so you can create energy, but you can only create energy if you destroy the equivalent amount of mass. Likewise, you can create mass, but it's going to cost you a tremendous amount of energy. So 9 times 10 to the 16 joules of energy must be used up in order to create 1 kilogram of mass. Okay, so there's a tremendous amount of energy equivalency in mass, and anyone who's seen footage of a nuclear bomb go off is simply observing an example of this fact. So I'm really getting ahead of myself. We're moving to outer and outer shells here, but I just want to clarify that even though mechanical energy is not being conserved, friction is not doing some magical thing and annihilating energy. It is simply converting mechanical energy into a non-mechanical form. Okay, so let's do another example. And what I want to do now is an example that involves 2 masses. So we've already done a problem like this. Let's suppose we have mass m1 connected to a frictionless pulley, no friction, by a string that then connects to a mass m2. And my question is, when m2 has fallen a distance h at what speed is each mass moving? So this thing, it's going to start off at an initial value of, actually let's let this be, let's call this MA and MB, because 1 and 2 are typically what we call the initial and final values. So MA and MB. Okay. So when MB has fallen a distance of distance h, what is the speed that each mass is moving? So this guy will have fallen down an amount h. And we're assuming that they start from rest. Okay, I didn't specifically say that, but they're released from rest. And I want to know how fast will this go. Now, we can use forces to solve this, right? And we've already done this problem, not with MA and MB, but this was a 6 kilogram mass and this was a 4 kilogram mass, and we calculated, I forget what we found the acceleration to be, but we can certainly calculate the acceleration in general for MA and MB, and then just use motion in 1D with constant acceleration. This guy's moving to the right at distance h, this guy's moving down at distance h, so we can certainly find out what the final speed is of each of those masses. But we're going to use mechanical energy conservation this time. So let's take a look at mass A, right? And mass A is going to move a distance to the right equal to h. So let's come up with our mechanical energy conservation equation for mass A. And what do we get? Kinetic energy, which is one half, well, K1 plus UG1 plus US1 is equal to K2 plus UG2 plus US2. Now, US1 and US2, there's no spring here, so we can just leave that alone. Initial kinetic energy is 0. Initial potential energy is 0. We can choose Y to be 0 here. For different masses, we can choose different origins. We can choose Y equals 0 to be here for mass A and here for mass B. This is equal to K2, which is 1/2 MA V2 squared plus 0 again. And the problem is that this now tells me that V2 is equal to 0. And this is not correct, obviously. As this thing slides to the right, it's going to have a velocity. So what went wrong here? What do we forget? Well, this is not a situation where the mechanical energy is conserved. There is work done by non-conservative forces. So we need to add that term. Plus work non-conservative on the left-hand side has to be there. So this becomes work non-conservative. So this is not correct. But what non-conservative force is doing work on this thing? Well, tension is acting on this mass, and this mass is not swinging, it's being pulled. So the work done by tension is what work non-conservative is. And what is it equal to? Well, work non-conservative is the work done by tension, which is going to be the tension force, which is F sub t, times the displacement, which is h, times the cosine of the angle between the two, which is 0 degrees. So it's just the tension times h. Okay. So, but I'm going to leave this as work non-conservative is equal to 1/2 ma times V2 squared. Okay. Now, this guy over here, MB. Starts up here, goes down here. V2, we don't know. V1 is equal to 0. This is H. So what do I get? I get initial kinetic energy, K1 plus UG1 plus US1. Okay, that's 0. Now I know that this has to be work non-conservative is equal to K2 plus UG2 plus US2. And work non-conservative, I'm going to prime work non-conservative because it's not going to be equal to the value from before. K1 is 0. UG1, let's take Y to be 0 here. So UG1 is going to be MB times G times H plus work non-conservative prime is equal to 1/2 mb V2 squared plus 0. Gravitational potential energy 0, right? So now what's work non-conservative prime equal to? Work non-conservative prime is equal to tension is acting up, displacement is down, times cosine of 180 degrees, which becomes minus Ft times h. But notice that this is, what do we get before for MA? Work non-conservative is Ft times h for this one. So this is the negative of work non-conservative for mass A. So now, what do we know? For mass A, we got work non-conservative is equal to 1/2 ma VA squared. And for mass B, we get MB times G times H plus work non-conservative prime, which is minus WNC over here, is equal to 1/2 MB V2 squared. So now mechanical energy for mass A is not conserved, and mechanical energy for mass B is not conserved. But the important thing to note here is that the work done by tension on mass A is the negative of the work done by tension on mass B. That's actually going to be convenient, because this means if we add these two equations together, what if we add the left-hand sides together? We get WNC plus MBGH minus WNC. I get MB times G times H is equal to 1/2 MA VA squared plus 1/2 MB VB squared. So once again, I added this equation to this equation. And what happened? The WNC terms canceled. So now what do I have here? On the left-hand side, I have the total, initial mechanical energy of the system. And on the right-hand side, I have the total final mechanical energy of the system. So to summarize, even though MA's mechanical energy is not conserved separately, and MB's mechanical energy is not conserved separately, the total mechanical energy of MA and MB is conserved. So that's what's happening here. This is the total mechanical energy before and the total mechanical energy afterwards. Work non-conservative cancels out. So this is an interesting, useful property. When you have two masses connected by strings and one moves as a result of the other, then you don't have to worry about the work done by the tension on each of the masses. If you examine the mechanical energy of the entire system, all you have to do is add the total kinetic energy of MA and MB initially, the total gravitational of MA and MB, the total spring MA and MB, there's no spring here, and set it equal to total final kinetic energy of MA and B and total gravitational final of MA and B. So this is all to say that we could have right away have jumped to so to summarize what I just did here in more general terms, I had KA1 plus U, well, let's do it this way, U, yeah, kinetic energy initial of object A plus U gravitational A initial plus U spring A initial, let's leave it like that, plus work non-conservative object A is equal to KA2 plus UGA2 plus work non-conservative, no, not work plus work non-conservative, that's done, and KB1 plus UGB1 plus work non-conservative B is equal to KB2 plus UGB2 separately, but if I add these guys together, I get KA1 plus KB1 plus UGA1 plus UGA2 plus work non-conservative A plus work non-conservative B is equal to KA2 plus UGA2, KA2 plus KB2 plus UGA2 plus UGB2. And what I'm telling you is that when you have two masses connected together, one pulling on the other, and they're connected by strings, then this is equal to 0. And what you simply get is K1 plus U1 is equal to K2 plus U2, but each of these is for both mass A and mass B. Okay? So, going back to our results, what do we get? Well, what do we have from before? There it is. So let's rewrite that. MB, what we're solving for, VA squared, this is not VA squared, this is, what did I do here? Sorry, this is V2 squared. Both of these are V2 squared. Sorry about that, shame on me. So rewriting that, how many of you were screaming at the video seeing that was written down before? All right, so MBGH is equal to 1/2 ma v2 squared plus 1/2 mb v2 squared. So this becomes 2 mb gh over ma plus mb square root is equal to v2. And there's my answer. Okay. So again, we solved this by setting the total for both masses, kinetic plus potential energy, equal to the same before and after. And in doing that, we didn't have to worry about the work done by tension. It just cancels out. All right, so that is pretty much it. At this point, we are at the end of the chapter on work, on energy conservation, and I believe the next topic, which is going to be covered on this upcoming Wednesday, is momentum conservation, or well, I'll tell you in a second. I think I'm wrong. It is gravity. Gravity. That's going to be on Wednesday, the 13th. Okay, but we're all caught up. So please make sure you have viewed this. Hopefully you will have viewed this lecture before Wednesday the 13th. Otherwise, you might have trouble with some of the material in that lecture. All right, and by the way, you will not be responsible for this material on the midterm. Right, the midterm only covers chapters 1 through 5. Okay, so that is it. Sorry for this inconvenience, guys. And as far as I know, the rest of the semester is going to be smooth sailing, and I won't be missing any lectures. All right, take care.